Good morning, everybody. In today's lecture, we're going to be following up with our discussions of how to compute settlements. And we're going to be talking more now about computing how long it's going to take for primary consolidation to occur. You may be looking at this figure and be wondering, what in the world is Dr. Frankie showing me on this figure? It looks like little snakes popping out of the ground. Well, we're going to talk about what these little things represent here later in this presentation. And it's a method of how we can speed up the consolidation settlement at a site. So I just want to remind you that geotechnical engineers are not just worried about how much settlement is going to occur, but how long it's going to take for that settlement to occur. Now, our geotechnical hero, Carl Terzaghi, he was the first guy to look at time rate of settlement. And he developed a theory to quantify and explain not just the magnitude of consolidation settlement. He also developed the theory of predicting settlement magnitudes. But he also used this theory to develop how long it's going to take for settlement to occur. And it's all based on conservation of mass, which is basically saying that, hey, the water going out in a given amount of time minus the water coming in at a given amount of time is going to equal the change in the volume of the soil, or in a given amount of time. So if we know what the change of the volume of the soil is, we are interested in knowing how long that's going to take. So in equation form, we can write it this way, where, again, the little v's here are going to be the velocity of the water, or the velocity of the water going in and out of the soil, and this big V is the volume of our soil element. So if we substitute in Darcy's law into this relationship, then we can simplify that nasty looking equation to a differential equation that's going to look like this, where U is going to be the excess pore pressure in the soil induced by the load that we put on it. Z is going to be the depth below the surface of our clay layer. T is going to be, of course, time. And then you see this little CV function. Okay, CV is what we refer to as the coefficient of consolidation, and it's a quantification that's going to make this whole calculation work. So if we solve that partial differential equation, there's really no direct solution. We have to come up with a numerical approximation, and it's going to look like this. And it's kind of scary looking, but don't be intimidated by this. We're not going to solve this solution per se. I'm going to show you that other people have solved it for you, and I'm going to show you some tools that you can use to take advantage of this equation, and just be grateful that you don't have to compute this equation. But a couple of things, for instance, U naught, for instance, is going to be the initial increase in the pore pressure at time equals 0. So when the load is initially applied, how much is my pore pressure going to increase? And we've already discussed in previous lectures that that's going to be equal to whatever my induced stress is that I put on the soil. So whatever my new total stress is that I applied to the soil, that is going to be what the pore water pressure takes at time equals 0. We already introduced Z. Now there's this term U sub Z. That's going to be the pore pressure at some depth Z. So here's my clay layer. And from the top of the clay layer down, that's going to be Z. So at some depth Z, when in the clay layer, it's going to be the excess pore pressure at that depth at whatever time we're interested in. M is an integer that we need to solve the equation. Big M is just a function of little m. We're going to talk more about this HDR term. HDR is the maximum distance that a drop of water would have to travel to get out of the clay layer. And so we'll talk about that in a slide or so, so just hang on to that. But what I want to introduce and talk about right now is this T sub V term that is called a dimensionless time factor. And T sub V relates to the coefficient of consolidation using this equation right here. So T sub V is a function of our coefficient of consolidation, and it's a function of the maximum distance that a drop of water would have to travel to escape from our clay. So the beauty of Terzaghi's approach is that we can get lots of useful things. For instance, we can get the pore pressure, or I should say the excess pore pressure, during consolidation, U sub Z, at any depth Z in our clay layer at any time. We can get the degree of consolidation. This is big U sub Z at any depth Z. And big U sub Z is equal to this equation right here, where it's just 1 minus the ratio of the incremental pore pressure at depth Z divided by the initial increase in the pore pressure at time equals 0. So think of it as almost like a status bar when you're downloading something. When it reaches 100%, your consolidation is completed. When it's at 0%, your consolidation just started. So that's what this degree of consolidation is. Now the average degree of consolidation is going to be the average degree for the entire layer. So look, this is important to understand. I've introduced to you a bunch of different U's. There's U naught, there's UZ, there's big UZ, and then there's U average. And we can get all of these from Terzaghi's equation. Remember that this is the initial increase in pore pressure right when our load gets applied at time equals 0. And it's equal to the induced stress that we put on the soil, so in that given layer. Okay? Remember that this is layer specific. Okay? U sub Z, this is going to be the increase in pore pressure at depth Z at time, at some time t in the consolidation process. And again, this is layer specific. So U sub Z is going to be anything less than U naught. So U sub Z started out at U naught at time equals 0, and then it starts going down from there. Eventually, U sub Z is going to approach 0 at time equals infinity. Big U sub Z, okay, this is the degree of consolidation at depth Z at time equals t. And again, that's layer specific. So it changes depending on which sublayer you're in the soil. Think of this again as your progress bar. How far along consolidation am I? 0% to 100%. It's going to be anywhere in between. The average, though, this is the degree of consolidation for the entire clay layer, not just sublayer. So this is not layer specific, this is the entire clay. So this is going to tell us not just that some depth in my little sublayer, but it's going to be the entire clay layer. What's the average degree of consolidation? And again, this is going to range anywhere from 0 to 100%. And so think of it like this. I like this little sketch. I'm gonna draw it. If say I have some clay layer. There's the top. I'm going down. Down is depth Z. Okay. And I'm going to draw a plot. So this is pore pressure. So when I come along and I apply some stress to this clay layer equal to delta sigma at time equals 0, my pore pressure is going to take that all the way down through the clay layer. And that's going to be U naught, and that's going to equal delta sigma. Okay? So in other words, if I were to plot that at time equals 0, my pore pressure, my excess pore pressure plot would look like that. Now, as I start the clock and start ticking time down, what's going to start happening is immediately water is going to get out, wherever it can. And as it starts to get out, that pore pressure is going to start to go down. And it's going to happen wherever the boundaries are, to the point where I'm going to have maybe something that looks like this now, where this value is going to represent U sub Z. So at any given value or depth of Z, I could come over and pick off, my value of U sub Z at that particular depth. Now, if I just focus on one particular depth, say this is my depth of interest, and I say at some time equals T, when this U sub Z line reaches 0, that means the soil is 100% consolidated. Okay, so what I need to do is this distance, that's equal to U naught. Whatever the distance is to wherever my actual U sub Z value is, that's equal to U sub Z. So that ratio U sub Z divided by U naught is going to be a ratio. So if I go 1 minus that, that's going to tell me how much, that's going to give me basically a percentage of how much consolidation I have left. Think of it this way. What if my consolidation line gets all the way down to here? Okay, if that's the case, then this distance right there is going to be equal to U sub Z, and so U sub Z is going to get really, really small, which means that that ratio is going to be small as well. So 1 minus a small little ratio is going to be something high, like 95% or something. So that's basically telling me that at depth Z, at that particular time, my soil is 95% consolidated. So that's big U sub Z. So erase some stuff here, and let's introduce what U average is. What if let's say now, again, I'm at one particular time, oops, let's get my axis back first. Okay, so let's say at time T, this is what my pore pressure distribution looks like. So again, that's U sub Z with depth, okay? So U average is just going to be the ratio of all the area in green that's still to the left of my line. divided by all this area in orange that was the original area of U naught. So that ratio of those areas is what U average is going to give me. So hopefully that little explanation will explain the difference between U, little u sub z, big U sub z, and U average. It's important that you guys understand the differences between those. So I promised that I would tell you what HDR is. Okay, imagine HDR, let's go back to this whiteboard. Here's my clay layer. Where would be, let's say that above my clay layer, first of all, I have sand, and below it I have sand as well. Where would be the location in the clay that it would take the drop of water the longest distance to travel to get into sand? It's not going to be here, because if it was right there, it would just have that little distance to go. If it was right there, it would just have that distance to go. So you could imagine the location in the clay would be right in the smack dab center. That means that in order to get out, I have to go either that way or that way, and both those distances are going to be the same. So if that's the case, this is what we call double drained. And that distance is HDR. Okay? Okay, so what's going to happen if, let's draw our clay layer again. Let's say up here we have more clay, something that is impermeable, and say down here is our sand. Okay, so in this instance, let's look at scenarios, some scenarios. If I go back to the middle of the clay layer, okay, the water is not going to drain up into this clay because it has nowhere to drain to. The upper clay layer is just as impermeable as the lower one. So it's going to drain down into that sand. But remember, HDR is, by definition, the longest drainage distance that a drop of water would take to get out of the clay. So that's not going to be the case for this scenario. In this case, a drop of water right on the boundary would have to travel the furthest to get out of the clay layer. So for this scenario, where we only have one boundary that is draining, that's going to be our HDR distance, and we call this a single drained clay, meaning that there's only one boundary on the clay layer that acts like a drainage boundary. And so when you have a single drained clay layer, the entire thickness of the clay layer is equal to HDR. So let's look at these two scenarios. Let's look at this scenario on the left. I have impervious rock beneath and I have sand above. So in this particular instance, the longest path that HDR would have to travel would be the total thickness of my clay. And we call this, again, single drained. On the example here on the right, I have gravel above, which is high draining, and I have sand below the clay, which is also high draining. So the water can squeeze out of the clay either above or below it. So this is going to be a double drain clay layer, and the furthest path that a drop of water would have to get out of it would be right from the middle of the clay layer. So it would be the thickness of my clay layer divided by 2, and that would give us, again, we call this a double drained system. Let's talk a little bit more about this parameter, the coefficient of consolidation, or C sub v. Now, C sub v changes with whatever the stress is that the soil is feeling. So C sub v is a constant parameter for the soil. It changes depending on the stress that the soil feels. So if we were to plot, and say we were to measure C sub V as a function of the stress that the soil is feeling, and we were to plot it with a corresponding consolidation curve developed from a consolidation test, here's what we would see. That the C sub V curve would show some sort of behavior like this, where we get a big steep portion of the curve that generally corresponds with the pre-consolidation stress. And up above, or in the zone where we're overly consolidated, that we have higher C sub V values, and places where the soil is normally consolidated, we have lower C sub V values. So what trends do we observe here? Well, first of all, we observe that we get higher coefficients of consolidation for over-consolidated soil than we do for normally consolidated soil, which means that over-consolidated soil consolidates faster than normally consolidated soil. And why is that? Well, because over-consolidated soil has a higher hydraulic conductivity and a lower parameter that we haven't learned about yet, but it's called an A sub V, and it has to do with the rate that the void ratio changes with the stress. We'll learn more about this in advanced soil mechanics. But just, I want you to understand that over-consolidated soil consolidates faster than normally consolidated soil because it has a higher C sub V value. The other moral of the story that I want you guys to take home from this little learning exercise is that you can't assume that C sub V is constant. C sub V, well, boy, that doesn't look very good. C sub V is not constant for a given soil. It completely depends on what the stresses are and what the stresses are going to be after you load your soil. So if you want to accurately predict how long settlement is going to take to happen, you need to be using the right C sub V value that corresponds with the stresses the soil is feeling and will be feeling after you place the stresses on the soil. So remember how I told you and introduced you to that nasty looking integral equation that was the solution of Terzaghi's one-dimensional consolidation theory? And I said other people have solved it, and I was going to introduce those tools and methods to you. Well, here they are. These curves represent the solution to Terzaghi's equation, and they have a special name. We call them isochrones. And what they represent is, think of these as the little U sub Z plots for a normalized clay layer. What do I mean by normalized? Well, it's normalized because the depth in the clay layer, Z, is normalized by the maximum drainage thickness, HDR. So that's why it's normalized. And the magnitude of our curves here, of our U sub Z curves, are normalized by the initial excess pore water pressure, which of course is essentially the same as saying U sub Z divided by the induced stress in the soil. It's the same thing, okay? And you're going to notice that each of these curves corresponds with a different time coefficient, 0.9, 0.8. These are all T sub V values. And so what is this saying? Okay. First of all, down on the bottom axis, we have degree of consolidation. So remember, again, that is 1 minus U so little u sub z divided by u naught, or 1 minus u sub z divided by our induced stress, delta sigma. So at T sub v equals 0, that means time equals 0. If T sub v equals 0, that means that our time equals 0. What's our percent, or what's our degree of consolidation? 0. It means that the soil hasn't consolidated yet at all. And right here, this is T sub v equals infinity. And if that's the case, then the degree of consolidation is equal to 1, or 100%. So this is how we can use then Terzaghi's equation in a very easy and graphical manner to get, again, little u sub z, big U sub z. But you may be wondering, well, wait a minute. I don't see anything that has to do with U average. Because I'm going to demonstrate to you another plot that we'll use to solve that. Let's erase some of my little text here so I can demonstrate what we're going to do. Now, if I'm using a single drained layer, remember that for a single drained, that HDR was equal to the thickness of the clay layer, right? So if HDR is equal to the thickness of the clay layer, and Z represents the depth that I'm into my clay, if Z equals the thickness of my clay layer, H sub T, meaning I'm all the way to the bottom of my clay layer, and HDR equals H sub T, then Z over HDR for a single drain is going to equal 1.0. That's going to be the maximum value that we would ever see for a single drain clay layer. And that's why I say if you have a single drain soil, you're only going to be using this portion of the isochrone that I'm highlighting right here, the upper portion. All this stuff down here on the bottom, you're not even going to use it, okay? But if you have a double drained, clay layer, remember HDR is going to equal the thickness of the clay divided by 2. And so if, again, I'm at the bottom of my clay layer in a double drain system, Z is going to equal the total thickness of my clay layer, because again, Z is the depth into the clay from the top of the clay. So if I'm at the bottom of the clay layer, Z is going to equal H, which is the thickness of the clay layer. If that's the case, then Z over HDR is simply going to equal H sub T over H sub T divided by 2, which equals 2.0. So what that means is that if I have a double drained clay layer, the whole isochrone is applicable to my soil. Okay? Now, I promised to give you a solution to solve the average degree of consolidation for the entire clay layer. And here it is. Now we can solve it either using equations. The problem is that there's no direct solution, okay? So it has to be broken up into two separate equations. There's an equation for U average from 0 to 60%, and then from 60 to 100%. And that's just because there's no direct equation that can be used to solve Terzaghi's formula. Or we can plot this graphically. So this portion of this curve that I'm highlighting right here, okay, that's 0 to 60. That's this guy right there. And then I wonder if I can change my color. Yeah. So then this blue portion of this curve That's this equation down here. And notice, friends, that it is all a function of T sub V. So U average and T sub V are the two things that are related, okay? And we can go either way. I can solve U average given a T sub V, or I can solve a T sub V given a U average. Usually we know T sub V and we're solving for U average. So in tabular format, these values right here shown in this table represent these values in this plot, okay? A couple of values I've shown or highlighted here that are important to us are going to be the T sub V value for 50% consolidation and the T sub V value for 90% consolidation. And I'll show you why in a couple of slides. So let's do an example time settlement calculation. Here we have a clay layer that is already in the ground, and we're going to come and we're going to place a brand new gravel fill on top of it. And the gravel fill is going to be 10 feet thick, and beneath the clay layer is a native sand layer. So both of those layers have high hydraulic conductivities and can act as drainage layers for our clay. From our consolidation testing, we're going to say that we're assigning a coefficient of consolidation of 25 feet squared per year to our clay, and our clay is 50 feet thick. What I want to find is, first of all, the percent consolidation at the midpoint of the clay layer after 5 years. So this is U sub Z, big U sub Z equals 25 feet at time equals 5 years. Then I want to find the average degree of consolidation for the entire clay layer after 5 years. So that's U average. And then I want to find the excess pore pressure at a depth of Z equals 12.5 feet below the top of the clay. So that's little U sub Z equals 12.5 after time equals 5 years. So those are the three things I want to solve. Okay, and we're going to use our isochrones to do this. So we need to solve our normalized depth parameters, Z sub HDR, to do this. So for part A, I want to go halfway down into my clay. If my clay is 50 feet thick, Z is going to be 25 feet. Let's point out too, this is a double drain system. If it's double drained, that means that HDR is going to equal half the total thickness of my clay layer, because that means that a point in the middle of the clay would have the longest drainage path out of the clay. Okay, so if HDR is 25 feet, then if we're 25 feet down to the middle of my clay layer and HDR is also 25 feet, then that ratio is just going to equal 1. Then if that's the case, I just am going to plug in numbers to solve for T sub V. So C sub V is 25 feet squared per year. That was given. Time is 5 years. That was given. And HDR is 25 feet. Don't forget the squared term. Some students make mistakes and forget that. Make sure you include that squared term in there. So our T sub V value is equal to 0.2. Okay? So what we're going to do is we're going to hang on to that. For part B, all we need to solve for that is our T sub V value. We already have it, so we're going to hang on to that. For part C, let's go ahead and resolve that ratio. This time we're at a depth of Z equals 12.5 feet. So Z is 12.5, HDR is still 25 feet. So our ratio there is now going to be equal to 0.5, and our time factor is still 0.2. So here we go. For part A, and our ratio equal to 1.0. Because we have a double drained layer, we're going to find where our T sub V factor was 0.2, because that's what we solved for. So there it is. And we're going to go to our depth ratio of 1.0. and we're going to come down, and we are going to get our degree of consolidation, and that's equal to, you can see right here where I'm circling, about 0.23 or 23%. Okay? All right, because we're here, let's just jump straight to part C. So part C, you recall that we're interested at the increase in the pore pressure at a depth of 12.5 feet below the ground surface. That ratio gave us a value of 0.5. And our T sub V factor is, because we're still dealing with time equals 5 years, so T sub V is still 0.2. So if that's the case, I'm going over to 0.5, and I'm coming over, and then I'm coming up, and I can see that my ratio here is going to equal about 0.54. Okay? Well, if that's the case, we know that my initial pore pressure is equal to my increase in stress, or my induced stress I put on the soil at time equals 0. And that's just going to be the stress from the new gravel layer I put on. The gravel layer has a unit weight of 130 pounds per cubic foot, and there's going to be 10 feet of thickness of it. So unit weight times thickness gives me stress, so that's going to be 1,300 pounds per square foot. So that means then that my pore pressure, my increase at pore pressure, is just going to be 0.54 times that initial stress of 1,300 psf. So I would expect at 5 years, at a depth of 12.5 feet down into my clay layer, that my excess pore pressure is a 702 psf. That means that of the 1,300 pounds per square foot that my load is applying to that depth in the soil, the water is still taking 702 psf of it. Okay, let's do part B. We're going to go to this curve right here, and you recall that my time factor was 0.2. So all I do is go up, and voila. From that curve, I can see that I'm about at 50%. If I wanted to, I could use these equations down here. The problem is that I don't know necessarily what my degree of consolidation is beforehand, so I don't know which one of those equations to use, and I have to solve both of them iteratively. Okay, I prefer just to use the chart, and you're good to go. Let's just say it like this, though. Use this equation right here. If your T sub V factor, let's see, is, I would say if T sub V is less than about 0.3, and then I would say use this equation right here if T sub V is greater than 0.3. That's a good rule of thumb. Okay, so that's how we solved those three parts of the problem. If you need to go back and review how we solved them, please, go ahead and go back in this presentation. Feel free to try to work these problems out yourself and to try to imitate and get the same answers that I did. Let's now shift gears and talk about how we obtained the coefficient of consolidation from an actual consolidation test. Now you'll recall from your lab experiments that you did last week that there were a couple of load cycles where you had to go and perform odometer measurements throughout the day, so you can see how the soil is consolidating with time during the day. And we use those time rate curves, that's what they're called, time rate curves, to compute or calculate what the coefficient of consolidation is. There's two methods I'm going to teach you. The first method is what we call the log of time method. In the log of time method, you're going to plot your time rate curve at your load cycle on a log scale. So time is going to be on a log scale, and deformation is just on a linear scale. Okay? So you have your initial deformation up here. I mean, that's before your test even started. And then you just plot your curve on that plot. So here's what we're going to do. Let's just move through these different steps. Step number one, we got to find what we call D100. This is the settlement or the deformation that corresponds to 100% of primary consolidation ending. What you're going to do is you're going to come to the steep portion of the curve, and you're going to draw a tangent line. And then you're going to come to the portion where we have secondary consolidation, and you're going to draw another tangent line. Okay? Where those two tangent lines cross, that's what we call T100. And the displacement or deformation associated with that is what we call D100. So step one is find D100 and T100 on your plot. Step two, we're going to pick sometime T1 near the top of the curve. I just recommend you pick the very first point on your curve. Whatever that is going to be, just make that T1, okay? But according to this little example that they have here, they picked some point B, and whatever, that's fine. To me, it's just easier if you just pick the first point on your curve. So you need to find T1, and then you're going to locate what we call T2. T2 is just going to equal 4 times T1. So then once you find T2, you're going to come up, and you're going to find the location on the curve that corresponds to T2. That distance between the value associated with T1 and the value associated with T2, that distance is what we call x. Okay? Step 3, we're going to draw a horizontal line, DE. We're just going to draw it all the way across our plot. And that line is going to be the same distance x above point B. Okay, so remember, point B corresponds to T1, but instead of going x below, now we're going to go x above. And that same distance, we're going to draw that straight line, DE, and that deformation is what we're going to call D naught. That's going to be the initial deformation before we applied our load. Why do we have to go through all that trouble? Well, the reason is because we can never get time equals 0 because it's a log scale. So, I mean, those first 3 steps are basically kind of wonky ways to approximate what the initial displacement was at time equals 0. Okay, step number 4, we now have D naught and we have D50. Divide them in half, D100. Divide them in half and get the deformation right in the middle. We call that D50. And then what you're going to do is you're going to come over to your curve and you're going to come down and find the time associated with that. And we're going to call that T50. This is the time it took for 50% of consolidation to occur in your soil. So we're going to call that point F, okay? The final step is we're going to use our relationship for T sub V, and for T sub V equals, T sub V and U average equals 50%. Remember, for T sub V, or U average equals 50%, T sub V is almost 0.2. It's actually 0.197. So we're going to use this equation right here to back calculate what C sub V would need to be to have 50% consolidation at time equals 50 and there's our T sub V factor of 0.197. This 1/2 inch, well, where does that come from? Well, remember, we're dealing with a consolidation specimen, and you cut that consolidation or that soil specimen to be 1 inch thick initially. So because it's double drained, HDR is going to equal 1/2 inch, or 1/2 the thickness of our soil layer. So that's where that 1/2 comes from. So that's how we do it. Okay, the second method is called the square root of time method. In this method, we're going to plot our time rate curve, but instead of on a log of time, we're going to plot it on a square root of time plot on the x-axis. So take the square root of your times and plot them on the x-axis, and deformation is still linear on the y-axis. Let's go through the steps now for this one. On step 1, what we're going to do is, well, we already said step 1. You're going to plot your time rate curve on a square root of time versus deformation curve. Now, step number 2. This is the tricky part, and this is the part that drives a lot of students crazy. The instructions say draw line AB through the linear portion of the curve. Okay, a lot of students will look at this and they'll say, well, that looks pretty linear. So they draw it right through the very early portion of the curve. That's not right. Okay, the correct way to say this would be draw it through the belly of the curve. So you see how when you do the log rate of time curve, it kind of has this curvy shape to it. What we're going to do is we're going to draw line AB right through the belly of the curve. We're going to eyeball it, folks. And you may go, well, wait, that seems pretty subjective. Like, I mean, is that repetitive? Is that consistent? Well, you do enough of these, you get pretty good, and you get pretty consistent. So we're going to draw a line AB right through the belly of that time rate curve. Okay, step number 3, we're going to draw a line AC. Let's change color for that one too. We're going to draw a line AC such that point C is equal to 1.15 of point B. So in other words, that distance between B and C is just an increase of 15%. We want the slope AC to be just 15% over from line AB. Okay? Then step 4, wherever line AC crosses our consolidation time rate curve, that crossing point right there, we're going to call that the square root of the time required for 90% of primary consolidation. So then now we're going to use again the T sub V relationship, and for 90% average degree of consolidation, T sub V is equal to 0.848, and we're going to back calculate and solve for C sub V. Again, there's the 1/2 inch, that's the HDR for our soil in the consolidation test, and T90 we're going to compute from this value that we circled over here. Okay, so you're going to want to be proficient with both of these two methods to compute C sub V values. So I have a couple of screenshots or examples of actual real life calculations to get C sub V from a project just in the Great Salt Lake here in Utah. Take some time, pause the presentation, and I want you to look at how each of these curves was drawn. So here's the curve for the log of time method, and go ahead and have a look at this. pause the presentation, and look how they did all the calculations, okay? After you're finished with that, you go to the next method. Here's an actual example from an actual project using the square root of time method. Go ahead and have a look at this one as well, and take out however long you need to kind of get a feel for what's going on with these curves, because you will be doing some of this on your own homework, okay? All right, so the last thing I wanted to talk about, we've covered a lot of stuff with settlement. In the last few lectures, we've covered how to compute how much settlement occurs, and in this lecture, we talked about how to predict how long it's going to take for primary consolidation settlement to occur. But here's the kicker. What if it takes like 5 years for a clay layer to experience primary consolidation? Nobody has 5 years to construct a new embankment or a new levee or a new dam. We can't afford to wait that long. And so you guys are all engineers. What do we do if the contractor approaches us and says, Mr. or Miss Engineer, here's the deal. You need to get all of the primary consolidation out of this soil within 90 days or within 60 days so that I can build, whatever it is I'm building and move on and get paid, and so you can get paid. So all of a sudden the problem is backwards now. It's not so much how long is it going to take for the soil to consolidate. It's we need the soil to consolidate in this amount of time. How do we make it happen? So I want to introduce to you two of the most common methods that we engineer the soil to achieve this purpose and to speed up consolidation and hit some target deadline that we need for consolidation. These two methods are commonly employed together, but I'm going to introduce them to you one at a time. The first is improving the drainage using what we call wick drains. Wick drains is kind of the layman's term for it. Really what they're called are prefabricated vertical drains. That's the more appropriate technical term, or PVDs is another name for what they're called. And so you have these machines that come in and they have these big mandrels, and they have these little devices. Let me just go ahead and draw a little cross section. So you have this kind of plasticky snake kind of thing that's really thin and flimsy. It almost feels like rubber. Now, if I were to zoom in on that, what I would see is this plastic material has little ribs in it, little ribbing. And that ribbing allows the water to travel along and get out. Travel along and get out. So water can move up those ribs and drain, pretty quickly. And so what these machines do is they come and they have a big roll of this stuff attached to these big mandrels, these big machines, and the machine grabs onto this roll and it pushes it down into the soil. And it has this sacrificial mandrel that once it gets down to the desired depth, it detaches from that mandrel and it just pulls itself back up, but it leaves this PVD or wick drain down into the ground. Then the technician cuts it right here. Let me just do that in black. Cuts it right there, and then the device moves over and does, another one. And just whatever the spacing is in the clay layer. Now, what's the advantage to that? Here's the deal. Let's say that a drop of water before the PVDs were in, the shortest distance to get out was that distance right there. And if we look at the equation for T sub V, remember T sub V is going to equal C sub V times time over HDR squared. Before we put any improved drainage in there, that HDR squared term is what was killing us, especially if we have a single drain soil layer, because HDR equals the total thickness of the clay. And that's what causes the clay to take forever to consolidate. But now, if we put these drains in, what now becomes the shortest distance for a drop of water to get out? It's no longer up, but now it's over. It's horizontally to the nearest drain, and once it reaches the drain, it's as good as out. The pore pressure is gone, and that water is out of there lickety split. And the other advantage that we have, do you remember how we talked about hydraulic conductivity? And I told you that the hydraulic conductivity in the horizontal direction is always significantly greater than the hydraulic conductivity in the vertical direction. So that's another mechanism that we have going for us. So we have two things going on with these prefabricated vertical drains or wick drains. We have shorter drainage distances. We're causing the water to drain horizontally now instead of vertically. And the second thing is that now we're taking advantage of higher conductivity, because we're forcing the water to move horizontally instead of vertically through the soil. So I have here a link to a video. I encourage you to either just type in this address, or if you go to Learning Suite and pull up this presentation under the completed lectures, you can click on this link, and it's a video, just a little 3-minute video or so, that shows an actual machine and technician working to push these things into the ground. And they're fast. I mean, they can push one of these drains into the ground, maybe 80 feet into the ground, in probably less than 2 minutes. And then they're on to the next one. And so it's pretty remarkable how quickly they can put these drains in the ground. And you remember at the very beginning of the lecture, I told you I would explain what all of this stuff was here in the field. Well, those are wick drains, folks. These are where the technicians cut the drains, and they're sticking out and are just down into the clay layer. And then these black lines that you see here, those are drainage lines that are just running along the site. And once the water leaks out of the drains here, they're going to get into these black drainage paths and travel along the paths and get out that way. So all of these drains, everything, are eventually just going to get completely covered in fill. And so those drains will be completely covered. You won't be able to see them anymore. But that's how we're going to speed up the consolidation of the soil beneath this particular site. So that's the first thing, okay? Improve drainage. The second thing is we're going to speed up consolidation by using what's called surcharge loading. And with surcharge loading, we're going to place an additional load or an additional induced stress on the soil for a temporary period until we achieve or exceed the anticipated amount of primary settlement. And then we're going to go back and we're going to remove the fill. Usually we exceed the amount of settlement so that we force the soil to be over-consolidated. When we force the soil to be over-consolidated, then the secondary consolidation settlement is going to go down, down, down because the soil is now over-consolidated. So why in the world does surcharge loading work? Well, it's pretty cool. If I were to plot, let's see, how am I going to plot this? If I were to plot time on this axis and I were to plot, say, settlement on this axis. Okay, let's say our calculations say that this value right there is going to be our total predicted consolidation settlement. Let's draw that line straight over. So that's our target. All right. So then what we show is that with time, there's kind of a rapid initially consolidation, and then it slows way down, and then eventually it's going to do something like this, right? So we would say, all right, consolidation occurs at this time. That's time 100. And that may be 5 years. That may be, 3 years, 2 years, whatever. It could be a really long time. Okay, so here's the idea behind surcharge. If I have surcharge, what if with the surcharge I predicted that, say, this amount of settlement right there was going to be my primary consolidation settlement with surcharge. So what's going to happen if I plot this consolidation curve is the soil is going to consolidate. It's going to follow the same kind of path, same kind of plan, and it's going to look something like this, where it's going to still take the same amount of time about to hit the total amount of settlement, or to get 100% consolidation. But notice here, remember, this was our target, and all of a sudden we surpassed it at a time much lower than the time to hit 100% consolidation before. And so what we do with surcharge is typically we go ahead and allow it to surpass our designed total amount of consolidation. We leave it on just a little bit longer, and then we take it off. So that once we take it off, say we bring it up and we take it off here, now our consolidation settlement is going to look something like this with time. That's the whole goal with using surcharge. So if I apply wick drains and I apply surcharge loading together, then we can really speed up the consolidation times, even for really thick, nasty clay layers that don't have very good drainage. So folks, I hope you found this interesting. Feel free to email me any questions that you might have, or go ahead and seek help from my teaching assistants, and they'll be happy to assist you as well. I appreciate your attention, and I'll look forward to seeing you in the next lecture. Thanks.